So, welcome to the Statistics and Data Science Innovations webinar series hosted by Membership and Outreach Committee of International Indian Statistical Association. Our today's guest speaker is Professor Rituparna Sen, and the title of Professor Sen's talk is Statistics in Finance. Dr. Rituparna Sen is an associate professor in the Applied Statistics Unit at the Indian Statistical Institute, Bangalore. Previously, she worked as an assistant professor at the University of California, Davis. Dr. Sen earned her BStat and MStat from Indian Statistical Institute and PhD in statistics from the University of Chicago. Her research area is the application of statistical theory and methods in finance. She regularly organizes workshops and training programs for capacity building in statistics and machine learning. Dr. Sen is the editor of Applied Stochastic Models in Business and Industry, ASMBI, and the associate editor of several other journals. She is also an elected member of the International Statistical Institute and a council member of the International Society for Business and Industrial Statistics. She has been awarded the Young Statistical Scientist Award by IISA, the Best Student Paper Award by American Statistical Association, and Women in Mathematical Sciences Award by the Technical University of Munich. Thank you, Professor Sen, for accepting our invitation and sharing your research with the IISA community. And without further delay, we'll start the presentation now. The floor is yours, Professor Sen. Thank you.
Thank you, Jyotishko, and thank you, Jyotishko and Sharik, for inviting me. It gives me a platform for sharing the statistics in finance, which I see is not much followed by IISA members. So I hope my talk will create some interest and people will start working. So, so my talk today is going to be mostly a review talk, a very broad talk. I will not go in deep into any papers, but I will present a lot of mainly my work only, but in different contexts. And anytime you feel free to stop me and ask questions, and I will try to finish a little early and keep time for questions. So statistics in finance. I'll start with, as a statistician, we do descriptive statistics and inferential statistics. That's how I planned my talk. And there are a lot of applications already, even in descriptive statistics in finance, which people can jump into. So I'll start with those, some of the works that I have done. And these are mostly not too technical. So these are works that I have done with summer interns or interns who worked over a whole year, so on. And then I will go into inferential problems, where I will talk about financial time series, and then multiple assets, and then things that are very common in the rest of the statistical community, also high dimensions. And something that is not so common in other places is high frequency. And actually high frequency is a very important, and sorry, there's something in the chat. 10 minutes at the end of So high frequency is a very important and essential area of finance. So I will present a few problems there. And then I'll take a financial approach. So these are kind of from the statistician's approach. And then from a finance person's approach, there are essentially three problems where quantitative methods are most useful. And these are option pricing, risk management, and portfolio optimization. So in the third part of the talk, I will take the approach of a finance person and talk about these problems and tell you where statistics is used in each of these problems, and also tell you a little bit about these problems themselves, because this community is mostly of statisticians. So I'll introduce that. So quite a big plan, as you see, but I will go really quickly on each of them. And as I said, feel free to ask me questions or later on email me. So starting with descriptive statistics. An interesting point is stylized facts. So what are stylized facts? These are some properties of stocks. So firstly, when I talk about finance, it's mostly about stock prices, although I will also talk a little bit about interest rates and so on. or exchange rates. Those are also in the purview of finance, but mostly we're talking about stocks, so which vary randomly over time. And there are some properties which are common to all the markets, irrespective of the nature of the stock. And these are called stylized facts. So whatever market you look at, whatever time you look at, certain things are common. And there are several papers on these. One nice paper that summarizes these is Quant 2001. And the current literature on the presence and identification of these is reviewed by Thompson, which is a more recent paper. And these things keep appearing. So why do we want to look at stylized facts? Well, one is, as statisticians, we want to build models which will help us do several things. I told the financial applications already there, or just to forecast things like that. So we want to build models. And if you want a model, then you want to know, what are the basic features of the data that the model needs to cover. And that is one of the reasons the stylized facts are important, that when you propose some model, then at least it should be able to explain most of the stylized facts, if not all. The other reason is that when you see one market, a new market maybe, and you want to see if all the stylized facts that have been observed so far are also true for that market. And if it doesn't, then you want to go into the economics of it, and you want to see how is this market different from the others. And this is very interesting because the data analysis that I will show you has been done in the Indian market. And we do see certain things that are different from the observations of the developed markets. So this is the paper that I wrote with Manavati, who did her full master's thesis with me, so 1 year of project. And this has been published, so you can go and read this up. What we did is we look at historical data, and this is available publicly. Generally, financial data, that is the first thing I think I should also talk about, because people who want to get into this also think about the data. So generally, historical data is publicly available, even Yahoo Finance, but these go to 5-minute or 1-minute intervals. If you want to get, the problems are in two cases. One is if you want to get data which is recent, like 2 minutes ago, so that becomes costly. You have to buy it. Data streaming, essentially, Bloomberg and all, they sell those things. And the other thing that is costly is if you want tick by tick data. So instead of whatever happens in 5 minutes, if you want very, very high frequency, whenever a trade takes place, you want to know it. That even historically, it is harder to get, and you often have to pay a price for it. And even harder is to get order book data, limit order books. So when not trades, but even quotes come in, people place bids and asks for trading in the market, and even that data is available, but those are generally have to be bought professionally. So we looked at free data, which was available in investing.com for 50 stocks, and we wanted to look at the Indian market. So we looked at the 50 that are included in the Nifty index. Like S&P 500, there is an index in India which is popular called Nifty. And for each stock, the data contains several attributes like trading day, name, date, closing price, opening price. And this was taken for a 10-year period, 2007 to 17. 11-year period. So this is how the raw data looks, essentially. This is price of, so we looked at end of day prices, daily prices, just end of day closing prices. So this is the end of day closing price for the stock Bosch. As you see that the raw prices themselves have some time dependence. There is some pattern over time, and that is something we do not want. So what we look at, what is customary in finance, and it is accepted that the time depend, so not autocorrelation, but I'm saying that they depend on time. At certain time period, something happens. So there's a trend, or even seasonality. So what one looks at is these log returns, and log returns are generally independent and roughly independent and normally distributed, and so on. So this is the log return of another stock called Bharat Petroleum, and as you see, this is more or less homoscedastic and stationary. So this will be the basis of the further analysis. And we have 50 stocks. And we look at these specific characteristics. One is aggregated Gaussianity, which is essentially CLT, that even though at high frequency, things may not be normal, but if you take a long enough interval, then they're approximately normal. And this comes essentially from CLT because looking at the returns and looking at a long time, we were adding up smaller returns. Although they're not independent, but kind of works, aggregated Gaussianity. Then there is volatility clustering. Volatility is the local variance. So what happens is, so essentially we will just look at the squared of the log returns. And what happens is, even though the log returns themselves are approximately independent, the square of the log returns has high autocorrelation, even for very high lags. So that is volatility clustering. The next thing we'll look at is the power law decay of autocorrelation of absolute returns. So the absolute returns autocorrelation goes down as a power law, and the exponent is generally in the range of 0.2 to 0.4. These are observations essentially that we are taking from literature. These are what are observed, and for our data, we will see if that is true or not. And then heavy tails with an index between 2 and 5. So this is also not reduced even after gauge fitting in most cases. So what do we see in the Indian data? Well, all these things are observed. The only difference is that in the developed markets that Pont describes, or several other authors later on, it is seen that if one fits a gauge model and looks at the residual, then the heavy tail feature goes away. But in the Indian data, it does not go away, even after fitting the gauge. The other more striking observation is the gain-loss asymmetry. So in most markets, what we see is that there are larger upward movements than downward movements. And the same phenomenon is also observed for European emerging markets. So this is what is observed in the Indian market. What is generally observed is the other way around, that there are, it has a longer, lower tail, that there are more, even after standardizing, there are more small movements and very less high movements. Whereas for the Indian stock, we see a lot of high movements. So maybe the Indian market is more optimistic or something like that, I do not know. So this is advantageous for investors because if you want to wait for a specific amount of gain, that wait time is shorter than the same amount of loss. So this is the first striking difference that we observed in the Indian market. The next one that we observed is that the leverage effect is reversed. So in most markets, the returns and the volatility are negatively correlated. So when the returns are low, there is high volatility. When market is not doing so well, then the market becomes very volatile. There's a lot of variance that comes in. But we do not observe that in the Indian market. So, and this has been seen also in some other places. Asymmetric gauge models have been developed to capture the negative leverage, but there are very few work on positive leverage. So we have to see why this is happening. So when there is, and again, this might have to do with the new market and a lot of optimism there. So if the returns are high, people go and just bid, and there is a lot of volatility that happens there. That is one of the possibilities. I don't know. I am not an economist, but these are the observations that we have. And the other thing that we observed, the last thing that we'll talk about this paper, is that 22 out of the 50 stocks that we studied showed significant autocorrelation in returns, whereas you expect the returns to be uncorrelated. But there is a lot of autocorrelation in the returns in the Indian market. That kind of points towards market inefficiency, that the market is not capturing all the information that is available, and therefore the returns are still autocorrelated, which is good for investors in a way that you have some signal, so you can actually make profit, or what is called arbitrage in financial literature. But it is not a good thing for the market. So the policy people need to come in, step in, and do something about this. Interestingly, I am right now doing another work with a master's student in South Africa. For the South African market, he studied the same things and he observed the same, he had the same observations. So he's still writing up his thesis, but these are the exactly same points where the South African market is also different from other markets and are similar to the Indian market. So what I'm thinking now is possibly do a big project of all the emerging markets and see if this is a feature of the emerging markets. Okay, so that was the first bit that I wanted to talk about. And then I go into what is called algorithmic trading. Now, this is mostly in the realm of machine learning because there is not much statistical, patterns, inference, models there. You just look at patterns and try to identify them and hope that they will continue in the future and try to make money out of it. So essentially, locally in time, you try to make money. So that is what algorithmic trading does. Try to develop algorithms which will identify these short-lived inefficiencies in the market, pick them up and use them to your advantage. So these are, as with all machine learning kind of algorithms, there is no guarantee or there is no error bound, things like that. So that is a problem. But still people are doing that everywhere. So I thought, why not? And with another intern, I did some work, but I will not talk a lot about that work. It's a little complicated. I'll talk more about the very standard algorithm trading so that you understand what happens there. So what this is called pairs trading. And what it does is you pick two stocks and so that their log returns have high correlation. And then you find the regression coefficient of one on the other. And then you see that you build confidence intervals for this error. And whenever in time, this confidence interval, the error goes beyond the confidence interval, then you make a trade. So when the error goes above the confidence bound, you sell Y and buy X. So essentially there will be some gain. Y is underpriced, you think, because log Y is smaller than it is supposed to be. So you are buying low and then you try to sell high. So when the error goes below, then do the opposite. So essentially you either buy low, sell high and or the other way around. And try to make a profit. So this is, and you see all these steps are can be done. So if you were doing a regression, you are building confidence intervals for the regression and you are kind of following it like in a statistical control chart kind of way. And whenever something happens, you take action. So this is pairs trading. And this is one example, and a lot of machine learning tools are being developed on several such algorithms. And this is statistical arbitrage is the name that is given to it. So using statistical properties to make money from nothing. Arbitrage essentially means you make money from nothing. So strictly the definition of arbitrage is that you make money out of nothing with probability 1. Here it is not that, the probability is less than 1. Because all these regression and confidence bounds, all these are not probability 1, but some probability thresholds are there. But still, this is called statistical arbitrage. Not arbitrage, but statistical arbitrage. So this is a paper that I wrote on a similar kind of thing, which is about index tracking. So there is the index. For example, I talked about the Nifty or S&P 500. You take some index, and then you have these constituents of the index. And one of the important things that as a practitioner of finance has to do in banks and all is to track this index, because the index itself cannot be bought or sold. So you have to buy or sell components of the index. Problem is that you do not know what the linear combination is that the index is using for individual stocks. So you have to come up with your own linear combination so that it matches the index closely, because people want to invest in some particular index. They want to have similar returns and volatility as the index. So it's one of the standard jobs of fitting index. And this is what we did. And we built these trackers. So these are quarterly rebalanced portfolios. And I am showing you the performance of these portfolios. So how much the value of each portfolio is at the end of each quarter. And we see that the Nifty is the dark line. And above that, I have a tracker with 10 and 10 and one with 10 and 15. What these essentially mean is how many of the constituents I'm going to take, which are, so when it is 10 and 15, I'm taking the 10 which are most correlated and the 15 which are least correlated. That helps, is what we found, instead of taking only the most correlated ones. So so we looked at these performances, the returns and the volatility and several other things. One can build portfolios out of these. So these are standard kind of work in algorithmic trading. Okay, now let us go into inference. Financial time series is a very important topic, and there are arch kind of models and stochastic volatility. There are questions of model selection, inference, forecasting. So very standard statistical econometric, financial econometrics. So all these people are doing such works. And yeah, it's a very common thing to do deal with financial time series. We are even teaching these things in our courses. So, the inference, another way is inference for discretely sampled stochastic process. So this is a little more involved because the inference is for you are observing prices only discretely whenever a trade is happening, but underlying there is a continuous process. So that inference often requires some special kind of handling. Why do we want to go into this whole model of continuous stochastic process? If our data is discrete, why don't we just look at discrete time processes? The reason is that the continuous time versions are very useful in the field of mathematical finance. So there is financial econometrics, and then there is mathematical finance, where one tries to price options and hedge options, which I will talk in the later part of my talk. So those are easier with continuous time models. So you want to have in mind, so you don't want to really throw away those. So you want to have an underlying continuous model and then deal with the data as discrete realizations of that. There are also issues of long memory, asymmetry, leverage, and these give rise to different kinds of Garch models. Nowadays, people are also, in addition to modeling the price, they're also modeling the volume and the duration. So all these are important problems and interesting problems in time series. So people who are already doing time series, I think, can look at the financial data, and maybe you can add a lot to the finance literature. Okay, so I go into multiple assets now. A lot of development has happened in copulas in the finance and econometrics literature due to heavy tails. So why do we need to look at copulas? Why are just bivariate normals, multivariate normals not enough? It's because the financial data have heavy tails. That is definitely one of the stylized facts, that they're not normal. Although maybe in the center, but not in the tails. The correlation is inappropriate as a measure of dependence. So other measures have to be studied. And extreme dependence and contagion is very important physically. Why is that? Because in the steady state in the market, maybe everything is going together or not going together. Things are almost uncorrelated. But when a bad news arrives, then suddenly all the stocks crash together. That is extreme dependence, that is contagion. And that is an important thing to capture. So network analysis is becoming popular in that. I have just started working with Shumanto on this of Cornell. So working on networks. But today what I will talk about is just extreme dependence in pairwise. So you have two assets and how they are related in the tails, even though they may not be related in the center. And okay, so why do we need a special work for this? Why is not, say, extreme values, tail dependence, those are enough? Because mostly they are looking at independent observations. In finance, time series is very important. But more importantly, what happens is that even if you have time series and a developing tail dependence, even there you expect that all the assets will crash together, okay, or all the assets will boom together. Okay, so all the extremes happen at the same point of time. Like if you look at extremogram of Richard Davis and so on. But what happens in finance is they don't crash together. So maybe one stock crashes today and the next stock crashes 2 days later. But still that is happening because of one is causing the other, and in general in the steady state market they would not have moved together at all, but they crash very close to each other. So what we develop in this work is essentially based on the waiting times between going below a particular quantile. So we see how long it takes for one stock to go below. So going below a particular threshold is the event, and we see the waiting time between those events for one particular stock, and that is what we call the recurrence time. And the other thing we look at is the residual time, which is given one stock has crossed the threshold, how long does it take the other to cross the threshold? And that is called the residual time. And what we look at is the distribution of the recurrence time and the residual time, and test if those distributions are same or not. So if these are same, then what that means is that one is not driving the other at extreme times. But if they're not the same, and which is what will lead to the rejection of the hypothesis, then one is driving the other. So this was done with data on, this is not very clear. These are several countries, and the position is pretty much as it is on the world map. So we see that, for example, India is not connected much with the rest of the world. So is Japan, it's quite away from everything, but China is quite well connected, and so on. So and this is the South America. So we didn't have data separately for the European countries. We also have arrows. So this becomes a directed graph, and that is what we are working on now. How to model this as networks, and how this network evolves over time. Does it detect strange periods for all the markets, and so on? So that is ongoing work. Okay. Going into high dimensions. Of course, high dimension is now, or has been for a while, very popular topic in all of statistics and in all of the applications. So here is one application in finance, and this is actually a paper that heavily relied on Jyotishko's work, and this was with Shorish. And what we're talking about is a sparse portfolio selection via Bayesian multiple testing. So again, I am not presenting much of the theory here, so I will just describe what we are doing. So the question is selecting a portfolio which will behave well. The problem is that you want the variance of the portfolio to be low and the mean to be, say, at a particular level. The portfolio is essentially a linear combination. So you pick, say, 500 stocks, and you have to decide where to put how much of your money. Okay, there are 500 stocks in the S&P 500. You can invest in any of them, in any proportion of your money you can put in any of them. Perhaps this is how our retirement income and all that is controlled. So they're being invested in this way. So it's important to invest properly over a long term, so that the portfolio keeps a steady rate of return, and doesn't have too much variance. So the rate of return is the mean, and the variance has to be controlled. But then when you have 500 stocks, or maybe even 2000 to invest from, then the covariance matrix itself becomes unstable, as we all know. So what we try to do is to pick a few of the stocks, and that is where we go into Bayesian multiple testing. How is this a multiple testing problem? We look at the capital asset pricing model, which tells us that if we look at any particular stock and at the market, as some index or something. So a particular stock is the Y and the market is X. And then we can take it over the values over time and do a regression, and it will more or less be a linear regression. What Shorish observed while working in SAS was that for this linear regression, most stocks have, if it is X equals alpha plus, sorry, Y equals alpha plus beta X, most stocks have alpha equals 0 and beta equals 1. So essentially, it is just a 45-degree line through the origin. They're behaving exactly as the market. Most stocks are behaving exactly as the market. It is only those stocks which are different can give our portfolio returns to be different from the market. So if it is exactly behaving like the market, we might as well invest in the market. So in the portfolio that we propose, we keep the market and we add only those stocks which are very different from the market, which means which have alpha not equal to 0 and beta not equal to 1. And that is the testing that we do. So alpha, beta, not 0, 1. And then it becomes a multiple testing because we do this for thousands of stocks. And this is our result. And you see the black line again is the S&P 500. That is the return of the S&P. It is the lowest. And any kind of picking of a few of these will help. So there are, the cap M is the red. And then we did large lasso. And that is the blue line. That already increases the returns. And then we went into the factor model with horseshoe prior and factor model with Bayes oracle. So of course the Bayes oracle cannot be achieved, that's the yellow, but the horseshoe prior factor model with horseshoe prior does very well. It has more than twice the return of all the other methods, including the large lasso. So we have a nice theoretical result as well as very good practical results, making money out of it. So, so that is one of the things that I wanted to present in high dimensions. Okay, and finally, I'll go into the last bit of thing in inference, which is high frequency, and I will actually present a couple of works here because this has been my area of research for a while. So what is high frequency data? You are observing prices as soon as a trade takes place. So that is the high frequency. Now, transaction prices are observed with noise. So you are not observing prices from a smooth continuous model like geometric Brownian motion as described in Black-Scholes or similar things, but you have some noise. And this noise happens because somebody places an order now and it gets traded maybe 2 minutes later, or there is not enough information in the market. And these are very short-lived, but still these are there. So there is some kind of friction in the market. And that gives rise to noise, and this is called microstructure noise. When we are looking at daily or monthly data, there is not much of a problem. But if we are looking at high frequency, then the contribution of noise becomes large, particularly when you are trying to estimate the quadratic variation. What the quadratic variation is essentially the sum of squares of the log returns taken over time. And then when you take the sum of squares, the part of it converges to the actual integrated volatility over a period of time. But then for every additional data point, you have a noise, and that adds up. And since this is like an integral or a sum and not an average, we don't average away the errors. The errors just keep adding and accumulating. So this is different from any other statistical, maybe not any other. There are a lot of people here from different fields. Maybe you see it somewhere else also, but I have not seen it anywhere else where the error adds up and doesn't get divided by n. So that is the big problem of high frequency data, that you want more data, but the more data you get, the more the noise accumulates. And yeah, so here are some reasons why there is microstructure noise. So this quantity, sum of the delta squares, and x is the log return, log price here. that is known as the realized volatility. And it is a consistent estimator of the volatility over the time period capital T. But in practice, this does not hold because the price is not observed, the efficient price is not observed, but there is some noise. And to see this, I will show you a picture where we take these grids and then move the grids around and take the average. So essentially the grid size is K. And so what we expect is when the grid size is smaller and smaller, you would expect the quantity to converge to the actual value. So this is the average realized volatility. And the convergence should be visible as K goes to 1. But if we look at this, and this is for real data of Facebook, July 6, 2020, for one whole day, I took high frequency data and I looked at this average realized volatility. And this is what I find. So when the frequency is low, these are in seconds, it is somewhere, and then it starts to increase, and then at ultra high frequency, it just shoots up. Okay? And then that is happening because I am adding these quantities, and each of these comes with error, and the errors just get added up. And one can show all these things theoretically also, but it's nice to see that it is actually exhibited in real data. So it's a real problem. So a lot of work has been done. I did something with Ananya, who is in IIT Tirupati now. And this is with the fractional Brownian markets, what happens to the realized volatility when the price is driven by a fractional Brownian motion. And it was interesting. We could derive theoretical results for where the noise is going and how it should be estimated, proposing alternative estimators which are consistent and so on. Another work in this area of high frequency is completely unrelated, is jump detection. So the stock price process is moving as more or less a smooth process. By smooth, I mean Brownian motion or fractional Brownian motion. So it's not very smooth, but still more or less. And then sometimes there will be market news. Maybe the government has fallen, and then there will be a jump. And one way of detecting these is to find intervals when the integrated volatility, which I described before, is significantly higher than at other times. So if you calculate this integrated volatility for several days and keep doing it for say a whole year, and suddenly on one day you see that it is very high. And then you will think that there must be a jump because a lot of these delta x's are much larger than a smooth model can explain. So first, of course, you want to model the volatility properly with GARCH and all. And then, so for the stationary part, you want to have a good model. And then you are trying to detect breaks in that. So this is another work in this line, modeling jumps and volatility in the Indian stock market using high frequency data. And we could find, so this is, I will just show you one output. We could find some particular days and times when there were jumps, and we could actually, many of them, we could relate to news. The union budget was declared, although there were some days when there was no specific news. And Reliance Communications launches mobile banking with SBI. So this is 2010 in India. And then this is interesting because these jumps are detected purely based on the data, and most of them except these two came with, later on we went and looked at the news and we saw that there was some particular news that was that happened on the day which might have caused that jump. So it's fascinating, essentially, as you're saying, to do research in finance because everything is so tied to practical real life. Okay, and then this is about asynchronous trading. And this is a more theoretical work, but the problem of asynchronous trading is very important and very interesting. So what happens is that we are now looking at multiples, say two stocks, and we are trying to find the correlation. And since we found the variance as these, sum of squares of delta x, for the correlation, a similar, a parallel quantity would be delta x times delta y. Now, when you're looking at ultra high frequency data, that is whenever trades take place, what happens is that the two stocks do not trade at the same time. Right? There is no reason for them to trade at the same time. So this is how they trade. This is Apple and this is Facebook. On the x-axis is time, and the triangles and dots, they represent the time when a trade takes place. So you see, for example, this whole interval, Facebook has had lots of trades while Apple hasn't had any. So if we look at delta x times delta y, if we call Apple y, then the delta y is going to be 0. And this is going to be true for all of these. In fact, since time is continuous, it is very unlikely that both stocks will trade at the same time. And not only once, but twice in succession. So probability is almost 0 that delta x times delta y is greater than 0. One of them is 0 when the other is non-zero. And therefore, if you look at high frequency data and find this covariance, which is called the realized covariance, that is going to converge to 0 as your sampling interval grows thinner. So even if you don't look at tick by tick, if you look at 5 minute, then 1 minute, then 30 seconds, as you go more and more to finer and finer frequencies, the estimator is going to converge to 0 instead of converging to the actual correlation. And so on one hand, you want more data, you want to go to finer and finer frequencies. On the other hand, your estimator is becoming inconsistent. So there is a lot of work already on this and how to handle this. Hayashi Yoshida is one of the common estimators that is used in this case. It kind of balances between how much data you take versus drop, and how much error you are making because of these non-synchronous things. So that is, and a lot of theoretical properties are proved for that, for jointly normal data or together moving as a geometric Brownian motion. So what we looked at is now with in a copula model. So we looked at Kendall-Stau instead of the correlation, and we needed to make this adjustment because otherwise, so you see the standard methods without any adjustments are previous tick and refresh time. So what previous tick means is that for every stock, you take the last time when it traded and take that as the price. Refresh time is you wait until all the stocks have traded at least once and take the price at that before that point for each of them. So these are standard ways of synchronizing data. And here in the left panel, the actual Kendall-Stau is 0.25, and these are the box plots that we got in simulations for the Kendall-Stau using these two methods. Whereas if we use our proper adjustment, which is a version of the Hayashi-Yoshida estimator for non-normal case, then in the corrected, and we also had to take into account some adjustment due to the waiting times. So there is a new contribution even in the proposal of the estimator itself. And we do get something that is much closer to the actual value. This is with rho equals 0.25, this is rho equals 0.8. So this paper also has been accepted in Shankha recently. Okay, so finally, I will go to the financial applications. And the first one is option pricing. So an option is a contract that gives the buyer the right, but not the obligation, to buy or sell an underlying asset at a specific time. And the first fundamental theorem of asset pricing states that if the market is arbitrage free, if and only if there is a risk neutral measure under which the price of traded assets are martingales. So essentially we use this, and therefore the price of an option at today is the expected price of the payoff at a later time. This is how we use the martingale to price options. And therefore, this opens up a huge opportunity for using probability and stochastic processes. Some problems in this direction are inferring the risk neutral measure itself. So I call this the risk neutral measure. What is it? It is not the physical measure that you observe in the stock prices. Because the fundamental theorem just says that there is some measure. So inferring that measure, finding expectations under this measure, mostly involving Monte Carlo, hedging options, which means finding a linear combination of stock and bond to replicate the option. And this can involve filtering techniques, finding bounds on option prices because there is some uncertainty in inference of the risk neutral measure. So various statistical probability problems exist in option pricing. And then there are variations in different directions because modeling can be done with different models. Fractional Brownian, as I've shown you, Levy processes. Now Hawkes processes have become very popular nowadays. Time varying volatility, time varying leverage. The type of option can be different: European, American, Asian, basket, barrier, what have you. The methods can include quantum computing, neural networks, robust methods. Criteria for what is a good hedge versus what is not, because often in the incomplete market, one cannot hedge exactly. So you can hedge in a quantile way, in a mean variance way, and any kind of combination of these. So a lot of papers being written in option pricing and hedging. This is something that I did long back. Hedging options in incomplete market with stochastic volatility, and maybe I just don't have much time. So risk management is the other thing, which means that you want to see how much loss your portfolio will incur in a given amount of time. So market risk is the change in the value of a portfolio due to change in the market prices. There could be liquidity risk, credit risk, various kinds of risks are there. I will present only something on market risk. Rate of change in the foreign exchange, change in the interest rates if you are doing multi-country things. Most commonly reported measure is the value at risk, and to tell statisticians what that is, it is essentially a problem of quantile estimation. So you want to estimate the quantile, which is at the lower, say 5%, 1%, whatever. So that is the value which your portfolio will cross only 5% of the time. And that is an important demarcation. Generally, by the Basel Accord, different policymakers, they require that you keep that much amount in fixed before you can make your stock public. So this is a problem of quantile estimation, and one can do parametric, non-parametric. There is time dependence. Various things can be done there. Another common approach is to fit a generalized Pareto on the tail. And so instead of going completely non-parametric, you do a parametric, but there are reasons why generalized Pareto is appropriate for the tail of stock prices. And so given more time, I could talk about that in a whole hour. And this is done using the hill plot, but there are issues of time dependence, robustness, and so on. So there is a lot of scope of statistical methods in risk management. Other risk measures are expected shortfall, which is the expectation of the return once it goes below the tail, so below the value at risk, below the quantile. And there are other measures like downside deviation, pain index, and so on. So various indices, estimating those indices, building confidence intervals. And finally, the question of optimization. And this is the last thing I'll talk about today. And it is to allocate a fixed amount of capital over many financial assets. I already talked a little bit about that large portfolio, the work with Shorish. But here maybe the portfolio need not be large, but even then there is the question of estimating the mean and the variance properly and doing the optimization. Of course, Markowitz did this work in 1952, but he assumed that the mean vector and the covariance matrix were known. But of course, they are unknown and they are also changing over time. So assets have time dependence. Portfolio can be rebalanced at intermediate times, and that can be helpful. So you want a dynamic model. So all these things can be done, and I will just finish with this last work, which is on Bayesian filtering for multi-period mean variance portfolio selection, where we start with a portfolio and then we incorporate data as they come in and use them in a filtering way and to update our portfolio. And the portfolio has a fixed time of expiration. So we see how much we can make out of that. And this picture summarizes it. So if we use a portfolio without Bayesian updates, here is the variance, here is the expectation. So for a particular level of expectation, it is good to have a low variance. But you see that this upper curve has a much lower variance than this red curve. So this red curve is the traditional without Bayesian updates. And this one, if we do Bayesian updates, we're doing much better. So this kind of looks like the efficient frontier is what it's known as. So the efficient frontier becomes much better if we are using, if we're updating your portfolio based on data that is arriving online. So here are some references. Thank you.
Thank you so much, Rituparna, for this excellent presentation. Personally, I can say that I learned a lot. So we have a little bit time for question and answer. If anyone in the audience have a question, please unmute yourself and ask. You can also type in the chat box and we can convey that to the speaker.
Thank you, ma'am, for the wonderful input. Ma'am, I'm coming primarily from the finance domain, actually, and I don't understand statistics that much as you do. And so, ma'am, actually, we do teach, like in behavioral finance, that, you know, because of this, what you talk about contagion impact, we refer to it as herd behavior. But how to capture this is something which I cannot understand that much. So, is there any statistical tool, because you were referring to contagion impact? So, I mean, it's in the normal terms, we refer to it as herd behavior. And there are various some, time periods within which we definitely find this herd behavior being practiced by retail investors. So, ma'am, what is the, way to kind of capture this?
Yes, I think the statistical literature there is lacking. And as I said, I am starting to work on that. The work I presented is really with two. So that is not herd behavior, but it does capture that feature that things happen only in the extreme and not during the stable periods of the market. But we are trying to extend that to multiple, particularly to very large networks. As far as I have studied the literature, there are a lot of work from finance, economics, observing this, but there is not much statistical work, I would say, to measure this contagion or to forecast contagion or to test for contagion. So these things are lacking and we need to work. So yeah, that is something that statisticians need to jump in and do these things.
Okay. Thank you, ma'am.
Mm-hmm.
Thank you. Any other question? So I have a potentially naive question. So when you, and it's about the high dimensional application. When you compare the lasso and horseshoe with the Bayes oracle, what's the metric that you're looking at?
That particular plot was only for the returns, but in the paper we also have the variance and the ratio of the mean to the variance. So all those things for different periods of time.
I think that is a very interesting work, because the Bayes oracle is not, I don't think it's developed for the regression context, and it's the only work that I know of where it's extended to the regression problem.
I had fun doing that, developing the theory, and it was so important practically.
Any other question? I see there is a question in the chat. If you want to take that. So there is a question about, will the recording be shared? Yes, we have recorded this meeting and we'll put this up on either our YouTube channel or the IISA website.
Something about Elsevier publication. I do not understand the question.
Dr. Selvi, if you could unmute yourself and ask the question.
Good evening, ma'am. Myself is Dr. Gangai Selvi, Associate Professor working in Tamil Nadu Agricultural University, ma'am. I want to know the experience you have observed from Elsevier publications, ma'am. That's why I'm asking. See, we are offering publication, you know.
And maybe
so now
we can
you are,
email me. This is not really pertinent to the topic of today's talk. So
okay.
I'll be happy to talk to you on email.
So if there is no other question, we'd like to conclude this webinar today. Thank you again, Professor Sen, for presenting your research. And we'll at the IISA, we'll look forward to the next webinar, which will be 1 month from now. And thank you. Thank you all for joining us.
Thank you. Bye.